and other. I think I forgot to press record. I'm sorry. It's all right. Other solvents and chemicals, etc. And it's quite a complicated picture because there's lots of different parts of this, and there are emissions being released at different places. So obviously there's emissions where we create energy and where we create plastic materials in chemical factories. But there's also things like methane released when we're extracting oil, and incineration of plastics at end of life that make emissions as well. And use phase emissions when we put fertilizer on the ground, and bringing these different accounts of carbon emissions together is quite challenging, obviously. Project has some different people, some from Santa Barbara in the States, Bath, a couple from Cambridge, Texas, Austin as well, and a company involved who has done a lot on chemicals in the past. So why? So firstly, chemicals are ubiquitous in our modern society. They're very attractive. We use them. It's mainly since the 60s this all took off. So the graphs on the right shows fertilizer production. And you can see it taking off from about 1960. The blue, synthetic nitrogen, and to the point now where half of the world is fed by synthetic nitrogen fertilizer, the other half by kind of more natural sources. Plastics at the bottom there, again, 1960s, huge growth in plastics, huge diversity, a lot of different products involved. And we expect that to go on. But the problem is obviously in a zero carbon world, it's really challenging to keep making a lot of these products. They're hard to live with, hard to live without. So just some facts there, 30% of final industrial use, 10% of global oil demand, 10% or 11%, 10% of natural gas, 17% of the industrial CO2 emissions are related to this petrochemical industry. And we're trying to provide these graphs breaking down across different types of petrochemicals and where in the life cycle they occur, the emissions. So it's kind of ongoing work. And I guess in terms of the sectors, the industry sectors, chemicals is the last really to be getting pressure from the climate change action world. So cement and steel have been under a lot of pressure. Electricity system, kind of has been done. Transport systems are under pressure. But chemicals are, I think, because of this very diverse nature, it's very heterogeneous, and traditionally they've been quite opaque. There's quite a lot of issues going on there, quite a lot of toxicity things that maybe have been hidden over the years, etc. And so it hasn't really translated properly. The kind of pressure hasn't really come through on the petrochemical industry. And when we kind of go in here, there's just loads of questions going on. People asking, should I use plastic? Should I use a recycled whatever? Should I do this? Should I do that? Government questions about how we use fertilizers, all sorts of issues. And not many answers, and a lot of misinformation, a lot of kind of New York NGOs saying let's just ban all plastics, and a very kind of, okay, so what are you going to paint your with? What are you going to, are you really going to have everything in metal tins again? And is that better for the environment? No, kind of. But at the other end, you've got this very strong kind of industry lobby, very well connected, very powerful kind of groups who basically just want to keep doing what they're doing, and are kind of saying, well, we'll do some CCS or we'll fix it up ourselves. So there's this real disconnect. So that's where the project is. We're coming to the end of it, and what I want to do is just present these key messages that have come out of the project. And each one of these messages, I guess, sit underneath that sits several papers that we've written. But it's interesting. What we're trying to do is think quite a lot about how you translate papers, which is our narrative, what we do, into messages for people that are more at the public or policy level. So that's a bit of a growth area, at least for meat. It's not easy to do. So the first one was reducing the petrochemical emissions is more complex than you think. We have been doing maps. So this is a previous map of petrochemicals. As a Sankey diagram, this is the hardest one to do by far. There's just hundreds of different processes. Every process has to be balanced in terms of reaction chemistry, not just mass, which is more challenging. And that's why we end up with all these secondary reactants, all these grey things coming in and out at the top, which is all the water and oxygen and CO2, etc. I won't go much more into the map. I mean, fossil fuels on the left there, coal, natural gas, liquid oil, refinery, through to fertilizers, thermoplastics, thermosets, fibers and elastomers, and solvents on the right, with all your kind of normal things that we'd recognize in there. It's a very complicated picture. Some work we've been doing, the Texas group has been doing, is looking at the US petrochemical. We're doing a network map here. So these are all different subproducts that are used to make products in the US petrochemical sector. And what we're showing here, the colouring, so all the grey is the background, and then the colour is the introduction of a single polyethylene recycled plant here. So it's a chemical recycling of polyethylene gets introduced here, and all of the colours is how that disturbs this network. And these are all companies that have got contracts and, transport routes between them. So really complicated, very highly kind of refined network that can, it's very hard to disrupt, I guess, and change. And we estimate that the capital involved in changing the network is 5 to 6 times the capital required just to build this polyethylene recycling plant. So fun work. This is kind of our kind of emissions account. So we've just published, well, the Nature paper that got rejected is getting better accounts of this chemical sector, 1.3 gigatons of carbon, and the 0.7, which is the upstream primary, and really trying to drill into that more. But just to show that it's a bit more complicated than that, if your plastic product is made from, in the States, from natural gas liquid, then it will have a footprint 3 times as high because of the methane released, due to methane. If your fertilizer is put on the ground, then the emissions are 3 times higher than just the kind of making emissions. So 2/3 of the emissions happen when you put the fertilizer on the ground as nitrous oxide, essentially. And if you incinerate your plastic end of life, the emissions are 2.5 times what this kind of making account is. So bringing those accounts together is quite challenging. So that's complexity. More of the nitrogen in the fertilizer needs to reach crops. So this is some work by Andre Sereno, my colleague. We showed this, half the world's fed by fertilizer, so you can't just get rid of fertilizer. But when we look at the fertilizer account, in a simple picture, we've got the synthetic 98 million tons of nitrogen, manure, and biologically fixed. And we need crop products of about 78, and there's 91 million tons of loss when we put that on the ground. So if we could remove those losses, we almost don't need any synthetic fertilizer. But the thing is, farmers like to put urea on the farm once or twice a year. When it doesn't rain, it does rain, and not maybe in the right place and next to the river where it gets washed away, etc. So huge losses, and that's probably where we should focus rather than upstream. And then we drew a Sankey diagram again. The details probably not important, but horizontal here is the nitrogen flows. At the top, we've got synthetic, this blue synthetic. At the bottom, we've got manure. So roughly about the same amount of nitrogen in each. And then the vertical flows are all the releases of emissions, greenhouse gas emissions. So manufacturing up here, but then all these N2O and decomposition emissions, which are much higher than the production ones. And interestingly, if you were thinking we should all go organic, use manure for everything, the emissions from the manure are actually higher per ton of nitrogen than the synthetic, because of the way a lot of methane and nitrous oxide get released when you mix manure. Burning plastics waste never makes sense. This is probably our most controversial one, because we're saying we shouldn't have incineration plants. Europeans love that message. If we look, this is European data here showing the increase of recycling and decrease of landfill over the years, and the increase of energy recovery, which is burning plastic essentially. So we've been kind of swapping out landfill for these two other methods. But when you burn a plastic, and these are based on the emissions released per equivalent megawatt hour or kilowatt hour of electricity generated, burning plastics in many cases is worse than coal. And certainly a lot worse than gas or the UK current grid or wind, which is much lower. So our idea that taking waste plastic and burning it in an incinerator is not a zero carbon idea.
And you're making these evaluations purely in terms of carbon here rather than other deleterious elements, is that right?
Yeah, I mean, yeah, interestingly, we've done a bit further work on that. In terms of toxicity, burning's worse as well, because as soon as you burn the plastic, you're releasing anything that's toxic in it, either into the air or it's landfilled. So about 20% of the residue is landfilled in a very active state. And the ash from incinerators is classed at the level of nuclear waste because it's so nasty. And then we stick that in the ground and wait for a river to come along and accept it and wash it away. So, yeah, we're not seeing this as an answer. And just, obviously, recycling is the priority here. But even this is some scenario we did with a consultancy, Systematic, and we published a paper there. Even at the kind of most aggressive recycling scenarios like this one, you're still seeing big chunks going down to landfill or leaking or being incinerated with CCS. CCS on incineration is really challenging because the incineration plants are never near where the CCS storage is. They're very dispersed. And so we think one of the answers there is to landfill plastics, which isn't a problem because you don't have any organics in there, so there isn't any of the issues around normal landfill. Maybe we call it long-term storage. Again, just with recycling, just showing that you can't recycle everything. There's always a maximum recovery point because the economics of capturing every last bit of plastic always go to infinity, theoretically. So there's some optimum level. We think it's about 50% of the plastics can be recycled. Increased transparency is needed for better decision making. This is some work that Luke was heavily involved with. You see, so we've both got the same surname, even though we're not related. So the papers are always coloured at the beginning, coloured at the end. Funny. So what we're doing here is we're looking at a number of different chemicals on the left-hand side, mainly plastics, but all plastic precursors. And we're looking at the data that you get in a life cycle assessment database. So carbon mines and eco-invent are the orange and the green line dots. So they're the numbers you use when you do an LCA. And then we're looking at this spread of possible numbers based on the top type of processes that can be involved. And you see these huge spreads of the emissions. This is on a log scale as well. So factor of 10 difference in the numbers. Actually, you're probably emitting. And the one on the right is looking just at ethylene. So this is 40 different processes for making ethylene. Again, the yellow and orange lines here are your your typical LCA database numbers that you'll use in an assessment. But you can see if you use coal, you use methanol to make your ethylene, the emission ranges are usually higher. I'm going to skip that at the moment and come back to that with Luke's stuff. And we've been doing this we're just trying to pull all this emissions data together in these dashboards. And this is an online dashboard where you can drill into where these numbers are, what regions and countries they come from, what type of plastics, and filter out what you want. And critically for us is putting emissions on these CO2 numbers. So we're doing a proper emissions account here. Replacing plastics with alternatives is worse for climate change in most cases. This is some work we did with McKinsey, and we've also published a paper now on that in S&T that's just come out about do plastics or do alternative plastics have lower emissions. And what we did is we took across plastic consumption. This is kind of a cumulative graph of plastic consumption, different types, packaging, building, consumer, automotive, textiles. We took representative products from across this, representing 90% of plastic consumption, and did life cycle assessments on them. And we're looking at the next best alternative. So these are all the applications like grocery bags, wet food packaging, soft drink, etc. This is the plastic material, and this is the next best alternative of what you can go to. And this is the difference in emissions here. And only steel industrial drums are slightly 30% better than plastic on emissions. Everything else is worse for the environment on emissions. And that was quite surprising, obviously, to see that, because I think the message there is if you're going to ban a plastic, you need to make sure no one uses an alternative in this place. Or the alternative message is just makes things last longer. So a plastic cup that lasts for 5 years is as good as a metal cup that lasts for 5 years. It's the throwaway nature of things that's the problem, the very short lifetimes. So really interesting on there that we need to be really careful with our policies.
Wouldn't just increasing the price be a price signal to to prevent the throwaway nature? I mean, I'm using these plastic, knife and fork, but I actually bring it with me each time. It's almost been 6 months since I'm using it. And,
but you're doing the right thing. Yeah?
I'm doing the right thing because I only use it until it breaks, but the thing is, most people don't, right? And so, but if these costs are pound each, then you probably more people would be, that would charge. The pizza is free, but the plastic costs you a pound. Price signal right now is out of whack, right? For most of for food product packaging, I noticed rigid packaging for food products. It's like what is it? The first vertical bar was rigid food product packaging, for which we basically pay nothing, right? It's not even considered to be part of the food, but if it were to be somehow priced in.
I mean, the beauty of plastics, the reason why we use them so much is because they're so cheap.
Right.
It is one of the beauties of I think that would help. I mean, I think there are clear things like if you moved from a plastic straw to using a metal straw, you probably need to use that metal straw for several lifetimes to pay off using plastic straws.
And not to speak of burnt lips.
Yeah, and all sorts. So yeah, and these are all great, but make sure you don't buy a new one every 3 months. A new water bottle. So
when these data is really interesting. I'm looking at wool, for example, for carpeting. Are you taking into consideration the whole animal's other use? So is it 80% if the sheep is only used for wool, or is it 80% after accounting for the fact that the sheep could be used for meat and for other things as well, and that the wool is not 100% of the carbon?
There's an allocation in there. I don't know the exact numbers, and that's why carbon accounting is always subjective, is because you have to make a decision about that allocation. There'll be an allocation in there. Yeah. But quite surprising and quite counterculture, again, getting us in lots of trouble. We need both supply and decarbonisation, supply decarbonising technologies and demand reduction solutions. So I think, you know, one end we've got this kind of decarbonisation industry view, just keep making as much of these materials as you can, and we'll solve it with CCS and maybe some direct air capture and some biofeedstocks in the future. And there's a lot of greenwash around that, and we believe that the supply solutions are just so limited on scale and pace. We're not seeing, you know, on one hand you've got the green glossy brochures of Saudi Aramco saying they're going to do CCS, but they're currently building plants that are not CCS compatible that will last for 8 years. So it's just there's a greenwash thing going on there, we think. But equally at the other end, you've got these calls for 100% reductions, plastic bans, 100% circularity, which are just dream world. You know, they break the rules of thermodynamics. You can't keep recycling things forever. In fact, plastics you can only really recycle once. And so the best you can get to is a 50% limited, because once you've recycled once, you basically are downcycling out of the system. So we think there's some solutions in the middle where you have to do a bit of both. We need this demand reduction. We need to think carefully about what products we don't need, what are the single-use stuff. We need to think about recycling. We need to think about maybe banning certain plastics. But we also need to think about decarbonising this industry as well. And at the moment, there are very polar views. We're seeing that with the plastic treaty negotiations at the moment. It's just like industry is here and the NGO world's here, and no one's got any data to even really trying to bring them together. Final one, inverting the carbon vector would deliver negative emissions. So this is very speculative, quite hard maybe to do. What we found when we looked at carbon, so carbon is a key building block of plastics. So decarbonising plastics doesn't really make sense because they're made from carbon. And you need to get the carbon from somewhere. And so the three sources of carbon are A, fossil fuels, B, recyclates, and C, kind of bio-based or direct air capture. Okay, on the left-hand side. If you're going to use, in a zero carbon world, if you're going to use fossil fuels, you have to sequester all the emissions along that supply chain, including incineration if you do that. And our sequestration, our CCS, we think is limited. I think there is a room to play for solid sequestration of plastic in the ground, which is much easier than sequestering gas, by the way. You know. The second is recyclates. So there's an input, you've got carbon and recyclates, which you have to recycle. There's a limit to how much you can. We're trying to get numbers on that. We think it's about 50%, but it's quite challenging to get it all back. Certainly, this is just plastics. Fertilizers you can't recycle at all, obviously. And then you've got bio-based and DAC, and we could argue and come up with some number about how much forestry we want to go into bioplastics. And direct air capture is very expensive at the moment. So I think we're limited there. And so we've got three stacks that are limited. If you're going to do incineration on the right-hand side, it has to be bio-based. If you don't sequester it, it's the only way you can balance the carbon. So with that, you've got these three stacks that we can put some numbers on what they're limited, and anything else has to come from demand reduction. So I think there is a route forward to thinking about that. When it comes to inverting the carbon vector, today we take carbon out of the ground and we burn it or release it as methane, or burn it, you know, energy we use to make the products or to burn in incineration, and it ends up in the air, which is not good. Sequestration thinks about taking that carbon out of the ground and finding ways to put that back into the ground, you know, as CCS or as landfill. Capture could think about taking like biostocks or direct air capture carbon, putting that into plastic, which means if you then released it and burned it later, that wouldn't be a problem, that would balance it. But we think there's a route for the future for the industry to be actually taking bio or direct air capture carbon, converting it in particularly around food and medical products, which are very difficult to get away from single use, and then putting those products into the ground as landfill and getting a negative source of emissions for capture.
But what about the plastic as construction material? I mean, replacing some bits of construction material with, that is sequester the carbon anyway.
You mean just leaving it in the ground or for long life?
Well, Lego bricks.
Yeah, or the pipe work that, all the plastic pipe that we put in under the ground, most of it doesn't get recovered.
Right.
And it will stay there for 80 years or whatever.
I mean, if you could, it has cinder blocks that are 20%
Yeah.
plastic, for example.
So I think that's a way of sequestering, yeah.
Right.
I think the volumes are quite huge at the moment. So my thought would be on the kind of landfilling, you clean, sort and store plastics. And then in the future, if it becomes economically viable or technically viable, maybe enzymatic recycling to recycle those plastics, you would have them as a feedstock. But if not, it's just like putting oil back in the ground.
But when you're talking about volume, you mean space. So what, Joseph, I think what we talk about is CCU, carbon capture.
Yes. But it's not carbon capture, just recycle plastic, we just, because then we use once, right? The second time around, just chop it up into bits, mix it in with cement, make it into a cinder block.
Yeah.
But the volume is about like the volume in land. So I was looking at CCU as for making huge building materials, making plastics, and the capacity, I mean, the opportunity was, the availability was huge, but it would actually use huge amounts of land.
Yeah.
And that's what you're referring to about volume, is that right?
Yeah, you would need to think about where you put it.
Huge.
And that's a problem for the UK.
Whereas if we store it underground, its volume issue is less spatial, is that right?
Well, it's still going to have to be holes in the ground that you're filling with plastic, yeah. So I think it's more challenging in the UK than it is in Australia.
Because of the cost of our land.
Yeah, we've just got none of it. We're much higher density, or Japan or Hong Kong is going to really can't make this. So, but I think yeah, CCU in buildings or in other places is interesting as well. Once you mix it with other things, there is no chance in the future you can recycle. So you've got to be quite sure, that you're not going to try and recycle it.
And then you start to think about the durability and the LCA life cycle assessment, how long you have it in use.
Yeah, as well. And in fact, you should be recycling all the single-use stuff and not recycling the long-term stuff anyway, because that's the dynamics that work better. Design, if your plastic's in a sewer pipe, you should design it to last for as long as possible. That's probably a better strategy, is to get it to 100 years than to try and make it recyclable. So that's the kind of key messages. And finally, I was just going to share a little bit, because Luke's been doing some work on this, and I guess this is just us thinking a little bit more about how we think about the data. So Luke's doing this project on graph representation learning for calculating supply chain emissions. So slightly different problem, but it's trying to work out where the emissions in the supply happen. We've got several ways at the moment of doing that. So we've got something for scope 3 emissions, which is the emissions over the supply chain. You can use monetary values and times them by metrics, or mass values and times them by LCA type metrics. And that's quite fast, but it's not very accurate. It's not self-improving. We can do life cycle assessments, which we go all the way down the product chain and try and understand the full impact of that. Very detailed, takes 6 months, costs 10 grand. So very precise, very slow, and not self-improving. So we've got these kind of problems there. And what Luke's trying to do is to use this graph-based work to try and come up with something that would be kind of much faster and precise and able to improve as you put better data in there. So that's what Luke can correct me if I'm wrong. We've been doing some work in MLBUs to complete emissions databases. So this table is quite complicated. We've kind of got a whole lot of different methods on the right-hand side coming down. We've got 3 data sets: UNFCCC emissions data set, that's the global one that's collected, climate trace, and our petrochemical model, and they're increasing features in those. And then we're testing these different models against them on 3 different levels. A problem where you're missing 1 year's time step, so you're missing 1 year in the data, you can interpolate between. One where you've got some emitters and you know there's another emitter that's a similar plant, but you don't know what it is or how much it's emitting. And then one where there's a lot more unknowns in there, you don't know anything about this other plant. And I guess the overview is to say that as you get more complicated, some of these ML tools are starting to be a bit more green. So down in here, we're starting to get slightly better results than the very simple tools up the top.
I mean, the second and third columns look almost the same, so adding unknowns doesn't seem to make things much worse.
Yeah, only fractionally worse, which is
Yeah.
It's also trying to communicate, so the whole kind of community that does life cycle assessment, material flow analysis is really only just starting to try and use machine learning. So it's very much to kind of bring together the ideas happening in the community that can machine learning be a tool in this kind of scenario, rather than solving a specific problem in this paper.
Yeah, and the results didn't all end up orange to green. So.
Yeah.
There is some when we're thinking about in these 3 different databases, what you would focus on, which feature is the most valuable to collect. So if you're missing data, in the UNFCCC data, it's the category of emissions that's important. In the climate trace ones, the capacity of the plant. And in our petrochemical ones, it's the product and the license of the technology. So if we can collect this data, we will be able to reduce our uncertainty on the kind of the calculation that we've got. We did some work on that. And then we did some work as well on if we have an emitter, so 0, which is the best other emitters to connect through. Where do we find the relative importance of the nodes around it? So is it that 2 facilities are owned by the same company, 2 facilities are making the same plastic, 2 facilities are located in the same region, etc., etc. Trying to understand across different levels of data how you can predict these emissions better. And this is kind of the vision, I guess, is trying to represent these supply chains as graphs. So we've got lots of data that we could collect here. So traditional Sankey diagrams like we're showing, but maybe some satellite data, maybe some other tabular data, cost data, shipping data from companies, etc. And we set that up with a prior belief on our graph. And then if we add more data, so some satellite data here about a facility, that reduces the uncertainty on that facility. But how does that propagate through to the other nodes? So we can say something about the uncertainty across, all the facilities. The idea being if we get some accurate data about a plant in Europe, we might be able to say something about a plant in China. Luke, did I explain that all right?
Sounded great, John.
Good.
Sign me up.
And so any questions, I guess, on the research, but also I'm really interested if you've got any ideas about how your type of techniques and tools could help us with some of these data challenges that we're trying to get to.
Before that, let's stand. Questions?
So I'm not answering your question originally to us, so I'm sure that others will engage with it. I work with Keshev in the Centre for carbon credits, and I also look for Cambridge Zero in their policy forum.
Yeah.
And I have a question particularly about how you look to create such really clear messages for policy. And the trade-offs and so on, but just how did you do it? If you could just give it that, but I'd really like a scoop to be able to get into your questions.
I don't know, firstly to say I'm very uncomfortable about doing this. I would much rather just crack papers and let other people read them and interpret them, but we're getting so much pushback now. I mean, I'm told that the policymakers can no longer read a paper because that's too long. And they
So
certainly,
I just.
they certainly won't read the
I'd like
100-page
to do
report.
that too.
So our first report was about a 150-page report, and we got absolutely slammed by this woman who said, look, 3 points was all you're allowed, kind of. And I don't think it's always our responsibility to boil down our research to 3 points so that some policymaker or politician can say something that's probably inaccurate and out of context anyway. But I do think we, you know, in a program like that, we had the money to try and push towards and maybe some higher messages that are backed up by these papers that we're writing and all the data, but we're trying to filter through. I don't know. We just tried to do them. We tried to refine them with the team. I don't know if they're going to be successful or not.
Well, they're certainly clear.
Well, thank you. Coming from a policy person, we're trying. We're trying.
I have also swallowed being a technical expert in something else, was realizing that senior people and the negotiators don't care.
Yes.
So they just need very simple, but with evidence behind it, very simple.
But we're trying to pull a little bit away from these very heuristic kind of plastics are bad and steel is good, or circular is good and linear is bad, or which are just so black and white and not. The picture is more complicated. I mean, even when you say plastics, it's hundreds of thousands of different products, materials. Each needs a different strategy for recycling, a different strategy. You know. So I don't know. I don't know how you deal with this complexity and this kind of preciseness. Yeah.
Any other questions?
I just have one thought about the data challenge you mentioned to use ML to complete the database you have. It just remind me of a previous talk, which is given by, I think, a postdoc from MIT doing the climate computing. So they're trying to use the 16-bit or 32-bit the numerical number to represent, you know, the 64-bit data, but the accuracy decrease, they still want to do the job. So we have the matrix, but which we want to approximate the most accurate 64-bit data, and then they try to figure out what's the best representation, or using the 32-bit, and given this matrix, and how to predict the next matrix, the number of that. So maybe there's some similar things.
It's sort of like a PCA, probably, principal component analysis, to say which are the most important features that you want to have. But I think you're sort of doing that, right? You said the 3 more things, most important things that you care about. So that was sort of what you're already doing, which fields give the most information.
Yeah, I mean, I think so. We've got a company we're working with. We've got 10,000 products, and they started off doing LCAs, and they've got a team of 50 people in India doing LCAs for them. They can only do about 50 a year, so 10,000, you're not going to get there. And that's where we've been thinking about the LCA approach doesn't prioritize anything. You go and collect up all the data as best as you can across the supply chain, and then you look at it, and half the things you collected will make no difference because they're less than 0.1%. A complete waste of time. So how do you prioritize your time to go after the big things? And I think using these kind of tools, you could get some kind of idea and infer what the emissions might be, work out what the big emissions classes are, and then go and ask specific suppliers questionnaires to improve that data point. The other thing with the company, obviously, they didn't have much CO2 data, but they do have all of their shipping data by mass, which they collect they have all their locations. So, you know, for instance, for example, for a steel product, we know a kilogram of steel is 1.5 to 2.5 kilograms of CO2 on average in the world, or, you know, that's the range. But if you tell me that the steel came from China, I can say it's 2.1 to 2.3. If you tell me it came from this region in China, I might be able to get down to 2.15 to 2. You know, so with information that's nothing to do with CO2 or making steel, I can get that uncertainty down. And so what other data do they have in an organization that we can use on different levels of this graph to get a better predictions of the numbers at the lower level of CO2? That's about as much as I understand the graph kind of stuff. So I think that's what we're trying to think about.
Yeah, I'm wondering about, you said 100% about uncertainty in the land use figure early on.
Yeah.
Like, what's that coming from? And could satellite stuff happen with it?
Yeah, I'm sure it can. That's just my friends in the IPCC who say these numbers are all over the place. There is a reason, as you think, so with emissions from, say, industry, it's this industry produced this much emissions, and we can kind of count how much coal they used. So plus or minus 5–10% probably is accurate. Okay, some companies will lie, some countries report bad statistics, but you know, we can get to a number. With land use, we're reporting the change. That's what land use change. And that change is on top of a massive lot of emissions that are being produced every year and a massive lot of emissions that are being sucked in, you know, so we're not counting the fact that we cut a crop down and it became CO2, and then next year we absorb that CO2 back into the next crop. So there's a huge amount of emissions that is just kind of going up and down. And there's a lot of uncertainty on the change, because that's, you know, whether you change from crop to cows or something, or, you know, those changes sit on top of a big absolute. That's why there's so much.
I think another way of putting it, I think Stephen Briggs, is that a huge amount of flux. You know, you have massive, like 100 going up and then 99 coming down. And the difference is the one that you care about. But you know, on one day it'll be 100 going up, 101 coming down. So it shows this beautiful visualization of carbon dioxide across Europe. Just I think every 5 minutes, every 10 minutes. In the morning, you know, you see it's all carbon emissions, and then during the afternoon, it's sucking down. And so there's a huge amount of flux going up and down, and then you try to find just a little bit of delta that was residual gain over the day and over a season, and it's just horrible. I mean, it's just really bad.
Yeah, that long-term average. And it's even harder if you're doing consequential LCA, which is what would be the consequences if I hadn't have converted this land into cows, because then your baseline is moving as well, and you're into really big, yeah. So there's a lot of uncertainty.
Any other?
Maybe this is more a question for Luke, but how is it that you construct these graphs that kind of codify the relationships between, I don't know, plants or like emitting sources, or like what does it mean that there's like an edge between two sources?
So, with some difficulty is the answer. So, you initially base it just on similarities such as they're making the same product, or perhaps they're owned by the same company and therefore have the same ways of doing things, or are in the same country and therefore are under the same regulations. And so initially you start with that, and then you refine it based on the importance that you see that certain similarities have. So, for example, when we saw like the prioritization of the data before, you see that, for example, the petrochemicals, just the product type is the most important thing to know. So the relationship between the different nodes will be the strongest when they're just sharing product rather than license or technology. And the way that you then calculate how some difference at node 1 affects node 2, given that they have that relationship, is the difficult bit. So it's kind of 2 steps. First, you kind of predict what the relationship should be. And then the second step is actually much easier. You just propagate the uncertainty, your standard kind of uncertainty propagation. You know what the value is here with some uncertainty distribution. you know what relationship is with some uncertainty distribution, and therefore you have an expectation at that node that you don't know. But the difficult bit is the first step of how do you establish the relationship if you don't necessarily know what the relationship is, and that's
Yeah.
when machine learning comes in.
Okay.
And I can talk to you in more in depth about it when.
That's really interesting. So the kind of the first step though, like before you've done this kind of feature importance analysis, is it's just kind of a handcrafted, like we think these three things, they're in the same country, they make the same product.
Yeah.
Generate a graph that satisfies those constraints.
Yeah, so you can easily generate like your initial graph.
Yeah.
And then it's how do you complete the graph
Yeah.
with the edges that you don't know the relationship of, and you don't have historical data for the nodes, so you can't calculate the relationship.
Yeah.
And we're still optimizing it right now. I've not actually
Okay,
found the perfect solution yet, but there's lots of different ways.
interesting. So then it becomes kind of a graph completion problem where you have all these sets of nodes and you're really not sure what the relationship is, and then the machine learning comes in for that graph completion.
Yeah, exactly.
Okay, interesting.
That's how we're thinking about it anyway. If you have any better ideas, please tell me. Within the next 2 months, because I'm waiting out at some point.
It's not easy.
I think we are a bit over time, so let's
Yeah.
stop with that. Thanks very much.
And you're welcome to talk to Grace or Luke or Scott, from my team.